I'm pleased to be here today with Professors Maria Flytzani-Stephanopoulos and Charles Sykes of Tufts University, who were selected as the winners of the 2019 ACS Catalysis Lectureship for the Advancement of Catalytic Science. Congratulations on the award.
Thank you so much.
Thank you very much. It's been really a pleasant surprise to hear about this, and we're both of us, I guess, very pleasantly surprised to get the call from you, Chris.
Maria and Charlie have contributed to the development of an interesting class of catalytic solids called single-atom alloy catalysts, both as individual researchers and as a collaborative team. Please tell us how the earliest work on this topic developed, stemming from the original concept to the first demonstrations of such materials in catalytic applications.
Yeah, so the idea actually came to me on probably a 6-hour drive back from Pennsylvania to Boston after a conference, and this was in 2006. I just set up my lab as an assistant professor, and I had a low temperature scanning tunneling microscope that could take really high quality images of surfaces. So I wanted to work on a problem that I could understand at the most fundamental level, but also had some applications in the real world. And I knew that metal alloys were ubiquitous all through catalysis, heterogeneous catalysis. So I decided to study different types of alloys with the scanning tunneling microscope. And I also knew about Jens Norskop's D-band model, where you can explain a lot of catalytic properties very simply by the electronic structure of the D-band. So my idea was to actually use the spectroscopic capability of the STM to go in and look at the electronic structure of every single different atom in the alloy, and in that way map out the D-band atom by atom. So I went back, and my students and I, Ashley Baber, Heather Tierney, we set up these very homemade sources for depositing tiny amounts of palladium into copper, into gold, and imaged that, and we were able to see all the individual atoms. And a real sort of lucky discovery came when we were imaging palladium atoms and copper at 5 Kelvin, and suddenly all these little depressions appeared on the image that were skating around on the surface. And I knew instantly from Wilson Ho's earlier work that that was hydrogen atoms. So I also knew that copper cannot dissociate hydrogen. And I also knew that there was only individual palladium atoms in this surface, so it must be that just individual palladium atoms in the copper surface could dissociate and spill over that hydrogen onto the copper surface. And that motivated me to then get funding to build other apparatus desorption equipment to really measure the energetics of uptake and release of that hydrogen, and also to go on to show that it is very active and selective in hydrogenation reactions.
For me, the introduction was really a realization that surface science and catalysis could be doing things together. That was the first step before the single atom alloys became part of my research. That realization came actually from the stuff I was doing at the time, which was single atoms of gold, for example, on ceria or iron oxide. And I had, on the iron oxide side, I had a collaboration with George Flynn at Columbia that really looked at a model catalyst of iron oxide, Fe3O4111, with gold atoms in it. And that instrument had high resolution, and that capability allowed us to see where the gold was, the gold atoms were, and where whether it would be stable there at high temperatures, and it was. So this was, for me, a capability that could be translated, could be transferred to catalysis, and that is how I started thinking that maybe surface science, STM in particular, would have a more prominent role to play. It was already in catalysis, but in my own research. And then Charlie came to Tufts. I mean, this was actually after Charlie had come to Tufts, but around the same time period, 2007, 2008, we were working with Flynn, and then I got exposed to the work that Charlie was doing, and the beautiful images I still remember of methanol that Ashley was collecting on gold 111. And all of that low temperature, much lower than what we're working with the model oxide catalyst. But it was important, it was a revelation again of sorts as to how these kinds of adsorbed species, and especially the sites where these things were, could be perhaps transferred to knowledge that we could use in catalysis. And that was the first. And then alloys I was not working on. But Charlie was in the alloys area, and then the thought that came to my mind was, what if there is a correspondence between atoms of metal atoms, say gold or platinum or on a support, that has the same chemistry when the atoms are in a metal host, like the stuff that Charlie was doing. I think that was the beginning.
Charlie, how did your background in surface science allow you to first conceive of single atom alloy materials and prepare the first examples of such materials?
During my PhD, I worked on the gold titania catalyst and model system of that. And this is something that's still even under debate these days, 20 years later. So it was a really complicated system: polycrystalline titania, gold clusters, oxygen, water, styrene. Really working in Richard Lambert's lab to try to figure out how this system worked, and it was fairly intimidating to work on a system that complex. So it was during my PhD I really fell in love with scanning tunneling microscopy, because you can see every single atom of the surface and you know exactly what it is. And that drove me to apply to Paul Weiss's group to work on low temperature scanning tunneling microscopy. And then really combining those two things, I always wanted to work on simpler systems, because the philosophy is you can always make a system more complicated if you like, but it's very hard to take a complex system and make it simpler. That's why starting on the single atom alloy concept, where you basically just have a perfectly clean surface, remove one atom, put a different atom, and that's your starting point. That was a very attractive system to start the study.
Maria, your expertise in catalysis by oxide-supported metals, amongst other topics, ideally positioned you to help push single atom alloy catalyst concept forward. What interested you in these materials, and what vision did you have for how they could offer opportunities for innovation in heterogeneous catalysis?
So I must say, if I reflect back to the early 2000s, that we had at that point discovered that single atoms were active sites in oxide supports. We did not have microscopy evidence for that, but we had spectroscopy. A few years later, advances in the aberration-corrected scanning transmission electron microscopy became available to us, and we collaborated with Larry Allard at Oak Ridge and got the first pictures. At the same time that we got, as I mentioned earlier, pictures or images from STM on the gold atoms on model iron oxide. So we had iron oxide model 111 Fe3O4, and then we model catalyst, you can call it, and then we had also the realistic catalyst, something we had purchased, showing in both cases stability of gold atoms in these matrices. So I put two and two together basically, and realized for my research it would be good to have both types of information to compare. And it was at that point, in about 2007, 2008, that I was also introduced through, you may say through students initially, to the work that Charlie was doing, and I got to see the images that he had, the new copper 111 model catalyst, again you may call it a catalyst, it is in the end, with the platinum or palladium atoms in it. And there was a student actually who was a senior, a very good senior in chemical engineering, who worked, did research with Charlie and had to have an advisor from chemical engineering. His name was Belisario, and he was the bridge, the initial bridge for me to go visit and look at the capabilities that Charlie's lab had in this area. That was, I think, the first part where I started talking to Charlie. And for me, in my mind, was this a really good time to marry the two, and through a real interaction, like maybe joint group meetings, talking to each other more often and so on. He was very open to that. I was interested, and I think that's how we came together around that time. Later was the real progress that was made, again with participation of students and a new person who came to chemistry, to Charlie's lab, to improve the capabilities, which is not just STM, but really we would have liked, and he did do that through George Kyriakou, who came and helped to introduce TPD. same chamber. So you do the STM, then you do the TPD, and you learn a lot. And at the same time, we could do this. We started making catalysts that could mimic the model catalyst in a single atom alloy. I'll talk about that in a minute. So Matt Boucher, who was my doctoral student, got really excited about this. And he worked almost for Charlie and me 50-50 at the time. And really, along with George, made this happen. And our first combined paper came out in 2012 in Science, describing this and describing these systems as novel catalysts that could do hydrogenation, selective hydrogenation of alkynes, for example. That was the first. And a year later, we came out with nanoparticles mimicking the model palladium copper at the time, doing exactly the same thing. How we did it in liquid, Boucher did it in taking under pressure, taking phenylacetylene to styrene, and that never went further, to ethyl benzene. So we had a very demonstration of the selectivity, and with nanoparticles that we had made in the lab, we were lucky to have the system copper, platinum, palladium at the time that we could prepare by the galvanic replacement reaction, which was easy, spontaneous. And so we had another paper and then a second in about 2 years time from the initial 2013-14. After that, we ourselves started getting much more going, but so did other people in the literature, in the community. They started publishing in this area. And so we feel very good about that. That it's all started around, the time that Charlie coined the term single atom alloys, and everybody noticed, I think. So.
Yeah, and just to pick up on your point about opportunities for innovation, theory, density functional theory, is really useful in this class of materials. As you know, heterogeneous catalysis, most of them are really complicated. They've got nanoparticles, different sizes, shapes, facets, dopants, promoters, everything. It's a real challenge to model that accurately with theory, whereas the single atom alloy is such a simple active site. It's just a planar surface, one atom's removed, one atom's added. You can model that on a tiny 2x2, 3x3 slab, and you can do a lot of very good density functional theory very quickly. So our collaborators, Angelos Michaelides and Mikhail Stamatakis at University College London, have really helped us out. We initially sort of benchmarked their calculations, but now they're predicting absorption energies on all these different alloys. And for example, the 7 we've tested so far, every single desorption temperature is within 10 or 15 Kelvin of their prediction. So we really trust the theory now. And they've actually gone a step further where they've looked at a library of 16 different single atom alloys and 5 different important reaction steps. And the things we've tested so far have worked just like they predicted. So we're now at the point where the theory can even lead the experiment, in the sense that if you have a reaction, you want to break this bond but not that bond, you look up one of these big tables and it tells you which the most promising single atom alloy is. So that's been a real opportunity for us, and we thank those folks a lot.
I would like to say, Charlie mentioned the theory, and really it is helping us, and it is the tripod, if you will, of the surface science, catalysis, and theory that is moving forward. And we are exploiting that very nicely with the collaborations that we have now. But it has become, again, evident to the community that this is the way to go. And we are, again, harnessing these kinds of bridges that you can form. And the bridges are 2 ways. In surface science and catalysis, because not many groups, or not many schools even, have the capability of doing both. We are fortunate to be so close in the same school. But it is a bridge that goes both ways. And you can actually, in catalysis, are totally different conditions. find something that works, a reaction that goes well on these types of single atom alloys, and then inform the surface scientists that this is the case, to then come to examine it in a model catalyst, and with the capabilities they have to really get us to or understand more the mechanistic parts of this. And then information, in other words, goes back and forth. A case in point was our butadiene hydrogenation that was first discovered on the nanoparticles as a very selective reaction that goes to butenes exclusively. And then this, because we could absorb and do reactions with butadiene at realistic temperatures and especially pressures, high pressures. And this information was then used by Charlie's group, and the two students that were one from surface science and one from our side in catalysis worked together, and we published on this particular area in 2015, 16, even 17. So Gile Yu from my side and Felicia Luzzi from Charlie's side are the co-authors of this paper. So the continuing collaboration through students also is very important, and it can happen once you have this ongoing. The other thing I want to mention is that there are issues of, that come now, another example. From the surface science, they can check for the issues of bifunctionality. How do these things work? Is it really a bifunctional catalyst? That can be addressed better by a surface science study than by catalysis, and you can get a more definitive answer. It is hard in catalysis to do bifunctionality study, and we have this example in our work coming from Charlie's side. Another thing is the stability, the selectivity, the issues, the reactivity and selectivity together with stability. How are these systems better, different than the traditional catalysts? We are addressing this, I think, efficiently and with the right focus in this collaborative work. So these bridges are good to have, and they work.
Maria, are these materials straightforward to prepare, or will their preparation and use under practical industrial conditions present additional challenges to be tackled?
I think in the lab they are very straightforward. We are doing these preparations in essence in air, and exposure to air is not a problem for most parts of the preparation. To make an easy way, the way we thought to make them originally, which could be even practical, is to make a colloidal solution, say, of copper nanoparticles. There are many established techniques in the literature for that. And once you have those, then you can support them on any support. You can burn off or do other things, not to let them grow too much, to remove the ligands from the copper. And then you can reduce again in another medium to introduce the second metal from a salt. For those systems for which this is a spontaneous reaction, such as platinum or palladium, the more noble metals as atoms or minority species in the metal host, we did that. We just put palladium or platinum from a precursor salt, and 1-for-1, which the atom of palladium for copper or platinum for copper would be replaced. And we could check that with UV. And so we established this technique as one that we commonly use now when it is, again, the right one to use. Other techniques exist, and many people can use or have used already other methods, such as you can do sequential reduction to put the second metal on, and you control the amount so that you have the composition that you set out to have. Again, knowing from the surface science how much really can be there in terms of amount of platinum or palladium as a minority, as a single atom isolated species in the host. There are other ways. Perhaps you can use unsupported metals, such as nanoporous materials. You can think of those. And Rani nickel that industry has worked with for decades is an example where you have some additives in it. You could use the same idea using copper, let's say, with additives and so on. That's another way. Many supports work, as I said, so depending on your reaction, as an application goes, you can pick and choose the kind of support that you would put. Doesn't have to be oxide, it can be carbon, it can be anything. So industrially, I don't think once these are proven to be the right way to go, industry would know how to do them. There is nothing really difficult or expensive in the making of these materials. What is interesting to check as we make them, it is how they evolve during reaction, how their stability is affected, and we also have information on that is very promising. Mainly that the stability of the isolated atom in that host is so good that it pertains, or it continues to be the same at high temperatures. And at high temperatures, you would more worry about the support, say the copper nanoparticle sintering, rather than the platinum atom coming out of the copper. Going subsurface also happens at high temperatures, but then you know how with molecules to extract these atoms to the surface. So I think the stability of a practical catalyst can be addressed with the proper either mesoporous type supports or proper template materials as supports of the nanoparticles themselves. So to my mind, the important new things here because how innovative are these catalysts, how new? They are new because they give you activity and selectivity at the same time that you can control the stability with independent ways. And that is really interesting or new and different in these types of materials.
Thinking back on your early ideas and hypotheses regarding single atom alloy catalysts, have any recent discoveries surprised you? And do these materials behave as you expected, or have you uncovered unexpected properties of these materials?
So surprises, absolutely. As a surface scientist, you're working in vacuum, you're working at pressures 13 orders of magnitude lower than the atmosphere around us. You're working on single crystals, so sometimes very different structures to everyday things, and also sometimes working at very low temperatures. So there's very few things you can discover or invent in a vacuum that will make it outside the vacuum and still be of the same composition. So in that sense, when we published our first paper, we demonstrated the reactions were selective in ultra-high vacuum. But as a pessimist, I never even thought to patent this idea because I thought, well, there's many hurdles you have to get over to actually make that a practical catalyst. And that sort of pessimism was unfounded because, Maria has showed in many examples, many single atom alloys work in reactors at temperatures as high as 400 or 500 Celsius.
For me, the synergies that we have realized in this research with the single atom alloys has been really a surprise, a pleasant surprise. We see the atoms having different properties, the way they absorb CO much more weakly than the extended metal to which they belong, the way they don't coke up. That was not expected. We found it on the way, and now theory comes to support the experimental findings. So these are new things that we have been, both of us, pleasantly surprised from, and we have also seen that not only the materials themselves surprise us, but what surprised me in particular is how the students and the people who are involved in this, who drive this research forward, they are communicating better, they are bringing as a team the whole thing forward, and this is something I didn't expect. So it goes both to the materials and to the work conditions that we have in the labs.
So another surprise came from the traditional view of metal alloys and catalysis, where you sort of think about a D band that affects the reactivity, and then you start doping in a metal and you shift that D band around and you tune it and you tune the reaction. that view goes out the window when it comes to single atom alloys. For example, John Kitchen a long time ago showed with theory that the electronic structure of the single atom dopant is there's no band. It's an atom-like state, and very recently Robert Schlogel has shown through experiment that it really is this unique atom-like state. The electronic structure of that dopant atom is much more like a single platinum atom in a vacuum than any sort of metal alloy. And that's what actually leads to this very local chemical reactivity where every single atomic site on the surface has a different energetic profile. And for example, a lot of the reactions, the transition state is above the atom, the intermediate binding site is at the side. So you actually decouple those two things and you can actually break linear scaling. So you can get both low activation barriers and weak binding and selective chemistry. So that's been a real learning experience for us to shift away from the sort of mean field argument of the older work. So that was a big surprise.
What drew you to study chemistry, Charlie, and chemical engineering, Maria, early in your career?
So I was naturally always drawn to the sciences where it's more about the concept, the equation, the model, the image. So I naturally was really interested in science, and particularly chemistry. I had a wonderful teacher in high school, Mr. Anderson, who really didn't just sort of teach you the textbook. He really taught you how to think about the subject and how to reason about problems you hadn't seen before. So in that sense, I really could excel at the sciences.
For me, chemical engineering at the time I graduated from high school was the top-rated school or department in the country where you could study chemistry. I also was interested in mathematics and physics and so on, so it made more sense for me to go the engineering side than the sciences at the time. I had no idea, where this would take me, but I went into it with excitement. And I never regretted. My subsequent degrees were all in chemical engineering. I discovered, the chemical engineering study was 5 years long, and in the elective courses, the ones I liked the most were those that had to do with the properties of metals, materials. So I discovered that back then. Went off to do a master's in statistical thermodynamics, totally different area. But it was my introduction to Lanny Smith's work at Minnesota, where I did my Ph.D., that really won me out of the theoretical stuff, I must say, to really try hands-on experience and work on metals and alloys at the time already, making single crystals in the tips of wires, of thermocouple type wires that you could put in flames, and the rounded tip that you get is really a single crystal. And on that study reactions like ammonia oxidation, like hydrocarbon oxidations, so on, and then model them. So that was really very exciting and fascinating to me. I wanted to stay in this area, and the stuff back then that we could do, SCM, of the time, with a low resolution, but still see the restructuring that was happening during the reaction at sub-micrometer level, not nanometer. And how this has translated to this day when we do sub-nanometer type resolution, we have even atomic resolution, we do these kinds of restructuring studies, and they are similar. You have the reversibility that I observed in my PhD coming back at that atomic scale now, the same. This is fascinating, continues to fascinate me. And I must say that I would have started, would I started today, I would have gone to the same, through the same path. I wish, I would learn more. Lanny Smith was great because he allowed me to stretch the limits in my projects, and that was very much appreciated, and I still have it.
What aspects of working together have you enjoyed the most, and what advice would you give young scientists who are looking for good collaborative projects and team members?
Yeah, so, traditionally the fields of surface science and catalysis have sort of existed without too much interaction. Some catalysis people also think, surface science is too fundamental or too removed from reality, so there isn't a good communication between the two fields traditionally. So I really enjoyed Maria as a catalysis expert, her total openness to basically write joint grants, do joint projects, and also having a great deal of patience with the timeline of surface science experiments that take a long time. So that was a wonderful sort of a bridging of those two gaps through this collaboration that I've really appreciated.
Yeah, I've also enjoyed this collaboration from the point of view of openness of both of us, and I thank Charlie for his openness in listening to the chemistry students, the problems they had, understanding some of the issues, and being so kind about it, and really, if you talk about patience, you have the more of the two. I have also enjoyed seeing the young people, the junior people in our groups collectively understand each other better, talk to each other, really have a common language now to communicate, which doesn't happen often. Again, it has traditionally been, as you know, separated. The field has these two areas, and for many years they were not talking to each other. Now we see in our groups how the chemists come to us in our joint group meetings, and they say afterwards, they said, "How did you think of doing all of that? It is too complex. How did you make it?" It is the preparation part, and then you test it under these conditions, and these types of things happen at these conditions, and we wonder, how relevant this is to what we're doing. And then the others from my group go over and they look at what is happening there in Charlie's labs, and they, with their eyes wide open, basically, in all of what they see and what they understand from seeing. So we've enjoyed that, and I think advice, as you said, what to do, I think it is telling them that this is how life is, professional life. They would have to work as a team. They have now the knowledge and the preparation to really do well as a team. And in this day and age, even academia or industry, but nobody can work really as an island anymore. So.
Yeah, and to add to that, I think sort of advice for younger scientists, collaborations are great, you should get into them, but you don't expect everyone to work. For every collaboration that works well, you may have 9 failed ones. That's certainly my experience. But failure of a collaboration is actually a positive thing. It means you're reaching out, you're looking for a difficult problem. If every collaboration works, you're probably not trying hard enough. So don't be afraid to start them, but also don't be afraid to end them if they aren't working well, because they're difficult things to manage.
Maria and Charlie, I will close by congratulating you on behalf of ACS Catalysis and the ACS Division of Catalysis Science and Technology on your selection as the 2019 lectureship winners. We are proud to add your names to our slate of honorees.